Hello there, and welcome to the Sleepy Science Place. I'm so glad you found your way here tonight. Maybe you've had a long day filled with earthly worries, or perhaps you're simply the kind of person who finds comfort in looking up at the stars rather than counting them like sheep. Either way, you've arrived at exactly the right place, at exactly the right time. Tonight, we're going on a journey together, not through space in any literal sense, but through the ideas and mysteries that make up cosmology, the study of our universe as a whole. And I promise you, there's something deeply soothing about letting your mind drift among galaxies and nebulae, about contemplating the vastness of everything while you're tucked safely in your bed. Cosmology invites us to think big, impossibly big, and sometimes that very vastness can quiet the busy thoughts that keep us awake. When you consider that the universe may be infinite, or that time itself had a beginning, your own worries can start to feel lighter, more manageable, almost like tiny stars in an endless night sky. So tonight, let's explore the cosmos together, gently and slowly, with no pressure to remember every detail. This isn't a test. This is simply a series of cosmic lullabies, facts woven into soft stories, designed to help you relax, let go, and perhaps drift peacefully into sleep. Before we begin our journey through the universe, if you're enjoying this content and you'd like to support the channel, please consider subscribing and leaving a like. It helps more people find these videos when they need them most. And if you have a topic you'd like me to cover in a future video, leave it in the comments. I read them all. But for now, just settle in. Adjust your pillow. Let your body sink a little deeper into your mattress. Take a slow breath in and an even slower breath out. The universe has been here for nearly 14 billion years. It's not going anywhere tonight. And neither do you need to be anywhere but right here, right now, letting the gentle rhythm of cosmic wonder carry you toward rest. Let's begin. Our universe began, as far as we can tell, about 13.8 billion years ago in an event we call the Big Bang. But despite its name, this wasn't really an explosion in the way you might imagine. It wasn't a bomb going off in empty space. Instead, it was the beginning of space itself, and time, and everything that would ever exist. Before the Big Bang, there may not have been a before at all, because time as we understand it didn't exist yet. Picture it not as a moment in time, but as the moment that created time, like the first note of an infinite symphony. And in that first incomprehensibly tiny fraction of a second, the entire universe expanded from something smaller than an atom to something vast, filling with energy and potential. You are, in a very real sense, made from that ancient moment, your atoms forged in the hearts of stars that came later, but originating from that singular beginning. As you lie here tonight, you're part of that story, a continuation of something that started so long ago. In those first few moments after the Big Bang, the universe was unimaginably hot and dense, a seething ocean of energy where particles and forces we recognize today were still forming. For the first few 100,000 years, the universe was so hot that light couldn't travel freely. Photons would scatter off free electrons constantly, like trying to see through a thick fog. But eventually, as the universe expanded and cooled, something beautiful happened. Electrons and protons combined to form the first neutral hydrogen atoms, and suddenly, light could travel. This moment is called recombination, and the light from that era is still reaching us today, stretched and cooled by the expansion of space, arriving as the cosmic microwave background, a faint glow in every direction we look. It's like a baby picture of the universe, and when astronomers study it, they're seeing the cosmos as it was when it was just 380,000 years old, still smooth and gentle, with only the faintest ripples that would someday grow into galaxies and stars and you. The universe is expanding, and it has been since the Big Bang, but what does that really mean? It doesn't mean galaxies are flying through space away from each other like shrapnel from an explosion. Instead, space itself is stretching, like the surface of a balloon being inflated. Imagine dots painted on that balloon. As you blow air into it, the dots move apart, not because they're moving across the rubber, but because the rubber between them is expanding. Galaxies are a bit like those dots. The farther away a galaxy is from us, the faster space is expanding between us and it, which means that very distant galaxies are receding from us at tremendous speeds. And here's something wonderfully peaceful to consider. There is no center to this expansion. Every point in space can consider itself the middle, watching everything else move away. You are, in a way, at the center of your own observable universe, looking out equally in all directions into a cosmos that's gently unfolding, always and forever. That expansion isn't slowing down as you might expect if gravity were gradually pulling everything back together. In fact, observations in the late 1990s revealed something startling. The expansion of the universe is accelerating. Galaxies are moving apart faster and faster as time goes on. To explain this, cosmologists have proposed something called dark energy, a mysterious force that seems to permeate all of space and pushes the universe outward. We don't know what dark energy actually is. It's one of the great mysteries of cosmology, but it appears to make up about 68% of the total energy content of the universe. Imagine lying in your bed, feeling the mattress support you, and then imagine that most of what holds up the entire cosmos is something we can't see, touch, or fully understand. It's humbling, really, and somehow comforting. A reminder that mystery is woven into the very fabric of existence, and that not knowing everything is perfectly okay. And speaking of things we can't see, about 27% of the universe is made of something called dark matter. This isn't the same as dark energy. Dark matter doesn't push, it pulls. It has gravity, and we know it exists because we can see its effects. Galaxies spin faster than they should based on the visible matter alone, and clusters of galaxies are held together by more gravity than their visible stars and gas can account for. Dark matter doesn't emit, absorb, or reflect light, which is why we call it dark. It passes through ordinary matter like a ghost, interacting only through gravity. You could imagine it as the invisible scaffolding of the cosmos, the framework upon which galaxies are built. Right now, as you rest here, particles of dark matter may be streaming through your room, through your body, completely unnoticed. They're part of the universe's hidden architecture, silent and unseen, holding everything together in ways we're only beginning to understand. It's as if the cosmos has a secret structure, and we're learning to read it like astronomers reading Braille in the dark. When you add up all the dark energy and dark matter, you find that ordinary matter, the stuff that makes up stars, planets, your body, everything you've ever touched or seen, constitutes only about 5% of the universe. 5%. We are quite literally a small chapter in a much larger story. The atoms in your body, forged in stellar furnaces and scattered across space by dying stars, represent just a tiny fraction of what's out there. And yet, here you are, aware and conscious, able to contemplate the universe that made you. There's something almost poetic about it, being both insignificant and precious at once, a small miracle of complexity in an overwhelmingly mysterious cosmos. As you breathe slowly and let your muscles relax, consider that you're participating in the universe's exploration of itself, one quiet moment at a time. Light has a speed limit, about 186,000 miles per second, or roughly 300,000 kilometers per second. This might seem incredibly fast, and it is by our everyday standards. But when you consider the distances in space, light actually moves at a gentle, almost leisurely pace. The light from the sun takes about 8 minutes to reach Earth, which means when you see the sun, you're seeing it as it was 8 minutes ago. The nearest star beyond our sun, Proxima Centauri, is about 4.24 light-years away, meaning the light you'd see from it tonight left that star over 4 years ago. And the farther out you look, the farther back in time you're seeing. The Andromeda Galaxy, our nearest large galactic neighbor, is about 2.5 million light-years away. When you see Andromeda, you're seeing light that began its journey when our human ancestors were just beginning to walk upright on Earth. Space and time are woven together, and every time you look up at the night sky, you're looking into the past, witnessing the universe's history written in starlight. Because of this speed limit of light, there's a boundary to what we can see, a cosmic horizon. The observable universe, the part we can theoretically see, is about 93 billion light-years in diameter. That sounds enormous, and it is, but it's important to remember that the universe itself may be much larger, perhaps even infinite. We simply can't see beyond the observable part, because the light from those regions hasn't had time to reach us yet. There may be galaxies, stars, and worlds beyond our cosmic horizon that we'll never be able to observe, entire regions of space forever hidden from us by the simple fact of distance and time. It's a little like standing on a shore, looking out at the ocean, knowing that there are places beyond the horizon you may never visit. The universe holds its secrets gently, and some mysteries are meant to remain just that, mysteries, drifting peacefully beyond our reach. The cosmic microwave background radiation, that faint afterglow of the Big Bang we mentioned earlier, is remarkably uniform. It has almost the exact same temperature in every direction we look, about 2.7 degrees above absolute zero. This uniformity was initially puzzling, because regions of the early universe that are now on opposite sides of the observable cosmos would never have been in contact with each other, given the speed of light and the age of the universe. So how did they end up at the same temperature? To explain this, cosmologists developed a theory called cosmic inflation, which suggests that in the first tiny fraction of a second after the Big Bang, much less than a blink, the universe expanded exponentially, far faster than the speed of light. During this inflationary period, space itself stretched so rapidly that regions that were once close together were flung far apart, carrying with them the same conditions. Inflation smoothed out the universe. Like stretching a wrinkled sheet, until it appears almost perfectly flat and even. It's a bold idea, and while we're still testing it, it offers a beautiful explanation. The universe may have started out chaotic, but in a flash it became the calm, ordered cosmos we observe today. Within that smooth early universe, there were tiny fluctuations, ripples of density that would eventually grow into all the structure we see: galaxies, clusters, superclusters, and the vast cosmic web. Think of these fluctuations as the seeds of everything. They were quantum in nature, small uncertainties at the smallest scales that inflation magnified to cosmic proportions. Over millions and billions of years, gravity amplified these tiny differences. Regions that were slightly denser pulled in more matter, growing denser still, while less dense regions became voids. Slowly, patiently, the universe assembled itself, like a garden growing from scattered seeds. The galaxies you see in images, the stars that light up the night sky, even the planet beneath you, all of it traces back to those infinitesimally small ripples in the fabric of space-time, long ago. It's a reminder that the grandest structures can emerge from the subtlest beginnings, that patience and time can turn whispers into symphonies. General relativity, Einstein's theory of gravity, tells us that mass and energy curve the fabric of space-time. The more massive an object, the more it warps space around it, and other objects follow the curves, which we perceive as gravity. Imagine a heavy ball placed on a stretched rubber sheet. The ball creates a dip, and if you roll a marble nearby, it will spiral toward the ball, not because of some invisible force pulling it, but because it's following the curve. On cosmic scales, this means that massive galaxies and clusters bend the space around them, and light from more distant objects follows those curves. This effect, called gravitational lensing, allows astronomers to see galaxies that would otherwise be hidden behind closer ones. The light bends around the foreground galaxy, reaching us as distorted, magnified images. It's as if the universe is using its own mass as a natural telescope, revealing hidden wonders. And in a quiet, metaphorical way, it reminds us that obstacles can sometimes help us see further, that bending around challenges can lead to unexpected clarity. Black holes are among the most fascinating and misunderstood objects in cosmology. They form when a massive star exhausts its fuel and collapses under its own gravity, compressing so much mass into such a small space that the curvature of spacetime becomes infinite at a point called the singularity. Surrounding this singularity is the event horizon, a boundary beyond which nothing, not even light, can escape. To an outside observer, anything falling toward a black hole seems to slow down as it approaches the event horizon, its light stretching and dimming, frozen almost in time. Black holes aren't cosmic vacuums sucking everything in. They only affect objects that come very close. From a distance, a black hole has no more gravitational pull than the star it came from. But at the event horizon and beyond, the rules of spacetime bend so dramatically that our usual understanding breaks down. Black holes are places where the universe's secrets are locked away, hidden behind a veil we cannot pierce, yet studying them teaches us about gravity, time, and the limits of knowledge itself. The universe has no edge in the way you might imagine. If you could somehow travel far enough in one direction, you wouldn't hit a wall or boundary. Instead, the universe might be infinite, stretching on forever in every direction, or it might be curved back on itself, like the surface of a sphere, so that traveling far enough would eventually bring you back to where you started. We're still not sure which is true. Current observations suggest the universe is very close to flat, in a geometric sense, meaning parallel lines stay parallel and triangles add up to 180 degrees even on cosmic scales. But this flatness doesn't mean the universe is a pancake. It refers to the geometry of space itself. Whether infinite or closed, the universe doesn't have edges, doesn't have an outside. It is, in a sense, all there is. This boundlessness can be dizzying to think about, or it can be freeing. There's no corner of the cosmos you could fall off, no end you could reach. You're held safely within a universe that simply continues, vast and gentle and complete. Time, as we experience it, flows in one direction, from past to future. But on the deepest levels, the laws of physics don't distinguish between forward and backward. The equations work equally well in both directions. So why do we remember yesterday but not tomorrow? Why does a broken cup never reassemble itself? The answer lies in entropy, a measure of disorder. The second law of thermodynamics tells us that in a closed system, entropy tends to increase over time. The universe began in a very low entropy, highly ordered state, and it's been spreading out, cooling down, and becoming more disordered ever since. The arrow of time, our sense of past and future, emerges from this journey from order to disorder. You are a temporary eddy of order in that flow, a beautiful complexity held together for a little while, before eventually returning to the cosmic background. But for now, in this moment, you exist, aware and alive, experiencing time's gentle current carrying you forward. There are regions of space so empty that they're called voids, vast expanses where almost no galaxies exist. These cosmic voids can be hundreds of millions of light-years across, enormous bubbles of near-nothingness surrounded by walls and filaments of galaxies. The structure of the universe on the largest scales looks a bit like a sponge or a web, with galaxies clustered along filaments and sheets, and voids occupying the spaces in between. It's a beautiful pattern, almost organic, as if the universe is a living thing with veins and chambers. Within these voids, a traveler, if such a journey were possible, would see very few stars, and almost perfect darkness punctuated by the faint glow of the cosmic microwave background. These empty spaces remind us that the universe is mostly emptiness, that matter and light are rare and precious, little islands of complexity in an ocean of silence. And in that silence, there's a kind of peace, a reminder that emptiness too has its place and purpose. Galaxies come in different shapes and sizes, spirals, ellipticals, and irregulars. Our own Milky Way is a spiral galaxy, with a central bulge and graceful arms curving outward, full of stars, gas, and dust. Spiral arms aren't rigid structures. They're more like traffic jams where stars and gas clouds move through, bunching up and slowing down before moving on. This gives the arms their shape, like waves frozen in place. Elliptical galaxies, by contrast, are smoother, more like cosmic eggs or spheres, filled with older stars and very little gas or dust. They may have used up their raw materials for star formation, or lost them through interactions with other galaxies. Irregular galaxies are just that, irregular, chaotic, often the result of collisions or gravitational interactions. Each type tells a story, a history of formation, evolution, and sometimes violence. But even in their violence, there's a strange beauty, a sense of natural process unfolding as it must, shaped by gravity and time. In about 4 billion years, the Milky Way and Andromeda galaxies are predicted to collide. Don't worry, this isn't a destructive crash in the way you might imagine. Galaxies are mostly empty space, and the stars within them are so far apart that actual stellar collisions will be incredibly rare. Instead, the two galaxies will pass through each other like ghosts, their gravitational forces pulling and stretching, swirling their stars into new orbits. Over millions of years, they'll merge, forming a new, larger galaxy that astronomers playfully call Milkomeda. Our Sun and solar system will likely survive this event, perhaps flung into a different part of the new galaxy, but essentially unharmed. By that time, humanity may not even exist in its current form, or we may have long since spread to the stars. The collision is a reminder that even galaxies are not permanent. They grow, change, merge, and evolve. But this change happens so slowly, so gently on cosmic timescales, that there's no violence, only transformation, a slow dance of gravity and light. The concept of a multiverse suggests that our universe might not be the only one. There could be other universes, separate from ours, each with its own laws of physics, constants, and perhaps entirely different structures. Some versions of inflationary theory suggest that inflation didn't happen just once. It may still be happening in other regions of a larger multiverse, with new universes budding off like bubbles in an infinite foam. In some interpretations of quantum mechanics, every possible outcome of every event might occur, each in its own branching universe. These ideas are speculative, and we may never be able to test them directly, but they remind us that reality might be far stranger and more abundant than we've imagined. If the multiverse is real, then everything that can happen does happen somewhere, and our universe is just one story among countless others. It's a humbling thought and also a comforting one. Whatever challenges you face, they're just one thread in an infinite tapestry, and you're doing just fine. You're doing wonderfully. There's no need to hold on tightly to any of these ideas. Let them wash over you like gentle waves, each one arriving and then receding, leaving you a little more relaxed. The universe is vast and patient, and so can you be with yourself. If your mind wanders, that's perfectly okay. If you drift off and miss a few facts, that's even better. It means you're letting go. Take a slow, deep breath in, filling your lungs gently, and then release it, feeling your shoulders drop and your body settle. The cosmos has been unfolding for billions of years, and it will continue long after tonight. Right now, all that matters is your comfort and your rest. Stars are born in clouds of gas and dust called nebulae. When a region within a nebula becomes dense enough, gravity takes over, pulling the material inward. As the cloud collapses, it heats up, and at the center a protostar forms. If the protostar gathers enough mass and the core becomes hot and dense enough, nuclear fusion ignites. Hydrogen atoms fuse into helium, releasing tremendous energy. The star begins to shine, pushing back against gravity with the pressure of its own light. This balance between gravity pulling in and fusion pushing out can last for millions or billions of years, depending on the star's mass. Our Sun is in this stable phase, and has been for about 4.6 billion years, with another 5 billion or so to go. Stars are engines of creation, forging heavier elements in their cores, and when they die, they scatter those elements into space, seeding future generations of stars and planets. Every atom of carbon, nitrogen, and oxygen in your body was created in a star. You are quite literally made of stardust, a fact that never loses its wonder. The life cycle of a star depends on its mass. Low-mass stars like red dwarfs burn their fuel slowly and can shine for trillions of years, longer than the current age of the universe. Our Sun, a medium-mass star, will eventually exhaust its hydrogen fuel, expand into a red giant, and then shed its outer layers, leaving behind a white dwarf, a dense, Earth-sized ember that will slowly cool over billions of years. Massive stars, however, live fast and die young. They burn through their fuel in just millions of years, and their deaths are spectacular. When a massive star exhausts its nuclear fuel, its core collapses in a fraction of a second, and the outer layers explode in a supernova, one of the brightest events in the universe. For a few weeks, a single supernova can outshine an entire galaxy. The core that remains may become a neutron star, incredibly dense, or if massive enough, collapse further into a black hole. Each stellar death enriches the cosmos, creating the elements necessary for planets and life. We owe our existence to these ancient stellar sacrifices. Neutron stars are among the strangest objects in the universe. When a massive star's core collapses in a supernova, protons and electrons are crushed together to form neutrons, and the result is a neutron star, an object with about 1.4 times the mass of the Sun compressed into a sphere only about 20 kilometers across. The density is unimaginable. A sugar cube-sized amount of neutron star material would weigh as much as a mountain on Earth. Neutron stars spin rapidly, sometimes hundreds of times per second, and they have incredibly strong magnetic fields. Some neutron stars emit beams of radiation from their magnetic poles, and as they spin, these beams sweep across space like cosmic lighthouses. When the beam points toward Earth, we detect it as a pulsar, a regular pulse of radio waves. These pulsars are so precise that they rival atomic clocks. Neutron stars are laboratories of extreme physics, places where matter behaves in ways we can barely comprehend. Yet they exist, scattered throughout the galaxy, silent and spinning. Quasars are among the brightest objects in the universe, powered by supermassive black holes at the centers of distant galaxies. As matter spirals into a supermassive black hole, it forms an accretion disk, a swirling disk of gas and dust heated to millions of degrees by friction and gravitational forces. This superheated material emits enormous amounts of energy, often outshining all the stars in the host galaxy combined. Quasars are most common in the distant, early universe, when galaxies were young and supermassive black holes were actively feeding. The light from the most distant quasars has traveled for billions of years to reach us, offering a glimpse into the universe as it was long ago. When you see a quasar in an astronomical image, you're witnessing a galaxy's violent youth, a time when black holes were gorging on matter and blazing across the cosmos. Now, in the nearby universe, Most supermassive black holes are quiet, having consumed the available gas, resting peacefully at the centers of galaxies, including our own. At the heart of the Milky Way, about 26,000 light-years from Earth, lies a supermassive black hole called Sagittarius A, pronounced Sagittarius A star. It has a mass of about 4 million times that of the Sun, yet it's surprisingly quiet right now, consuming very little matter. Astronomers have observed stars orbiting close to Sagittarius A, moving at incredible speeds, their orbits revealing the black hole's immense gravity. In 2022, scientists released the first image of Sagittarius A*S event horizon, a glowing ring of hot gas surrounding the shadow of the black hole itself. It's a remarkable achievement, capturing something invisible by seeing the light around it. This black hole has likely been at the center of our galaxy for billions of years, a silent anchor around which hundreds of billions of stars orbit. It's a reminder that even the Milky Way, our home galaxy, has depths and mysteries, a dark heart holding everything together, patient and ancient. The cosmic web is the large-scale structure of the universe, a vast network of filaments made of galaxies and dark matter, surrounding enormous voids. If you could step back and see the universe from the outside, if such a perspective were possible, you'd see this web resembling the neurons in a brain or the structure of a sponge. Gravity pulls matter together along these filaments, and where filaments intersect, you find massive galaxy clusters. The web formed over billions of years, shaped by the initial tiny fluctuations in the early universe and sculpted by gravity and dark matter. It's a beautiful pattern, a reminder that the universe has order on the largest scales, even though individual galaxies and stars may seem randomly scattered. This structure suggests that the cosmos is not chaotic, but rather follows deep, elegant rules, creating patterns that repeat at different scales. There's something comforting in that, knowing the universe has a shape, a structure, a coherence that persists across billions of light years. Galaxies themselves are not evenly distributed. They form groups and clusters bound together by gravity. Our Milky Way is part of the local group, a collection of more than 50 galaxies, including Andromeda and various smaller dwarf galaxies. The local group, in turn, is part of the Virgo supercluster, a larger structure containing thousands of galaxies. And even superclusters are organized into larger structures along the cosmic web. On the grandest scales, the universe looks almost uniform, but zoom in a little, and you see hierarchy. Stars in galaxies, galaxies in groups, groups in clusters, clusters in superclusters, superclusters along filaments. It's structure within structure, like nesting dolls made of light and gravity. This hierarchy emerged naturally from the laws of physics, from gravity acting over time, shaping the universe into a place where complexity can exist, where galaxies can form, where stars can shine, where life can emerge and look up and wonder. Redshift is a key tool in cosmology, a way of measuring how fast distant galaxies are moving away from us. Light is a wave, and when a source of light moves away from you, the waves stretch out, shifting toward the red end of the spectrum, hence redshift. The greater the redshift, the faster the galaxy is receding. By measuring redshift, astronomers can determine not only a galaxy's speed but also its distance, and because light takes time to travel, how far back in time we're seeing it. High redshift galaxies are the most distant, their light stretched by the expansion of space over billions of years. Observing these galaxies is like opening a time capsule. We see them as they were when the universe was young. Redshift turns light into a messenger, carrying information across the cosmos, telling us the universe's story. And as you lie here, the light from those distant galaxies is still traveling, still on its way, some of it destined to arrive long after you and I are gone. The cosmic microwave background isn't perfectly uniform. It has tiny variations, hot and cold spots differing by only about 1 part in 100,000. These variations, detected by satellites like COBE, WMAP, and Planck, are incredibly important because they represent the seeds of all structure in the universe. The slightly denser regions grew into galaxies and clusters, while the less dense regions became voids. By studying the pattern of these fluctuations, cosmologists can learn about the universe's composition, age, and geometry. It's like reading the universe's baby picture and inferring its entire future. The fluctuations themselves likely originated from quantum fluctuations in the very early universe, microscopic uncertainties that inflation stretched to cosmic scales. The tiniest quantum jitters became the blueprint for galaxies, stars, and eventually, you. It's a profound connection between the smallest and largest scales, a reminder that everything is linked, woven together across time and space. One of the great mysteries in cosmology is the Hubble tension, a disagreement between two different ways of measuring the universe's expansion rate, called the Hubble constant. When astronomers measure the expansion using the cosmic microwave background, they get one value. When they measure it using distant supernovae and other objects, they get a slightly different value. The discrepancy isn't huge, but it's significant enough that it can't easily be explained by measurement errors. This tension suggests that we might be missing something in our understanding of cosmology, perhaps something about dark energy, or the universe's history, or the nature of expansion itself. It's a puzzle that cosmologists are working hard to solve, and it reminds us that science is always evolving, always questioning. Even our best theories have gaps, and that's okay. The universe is still teaching us, still revealing surprises, and there's a kind of excitement in knowing that we don't have all the answers yet. The Planck epoch refers to the earliest moment of the universe we can theoretically describe, from time 0 to about 1043 seconds after the Big Bang. During this unimaginably brief instant, the universe was so hot and dense that our current theories of physics break down. Gravity, electromagnetism, and the nuclear forces were likely unified into a single force, and spacetime itself may have been a quantum foam, fluctuating wildly at the smallest scales. We don't yet have a theory of quantum gravity to describe this era, so it remains speculative, a frontier of theoretical physics. But imagining it, a universe smaller than a subatomic particle, containing all the energy that would become everything, is strangely beautiful. It's the ultimate mystery, the origin of origins, a moment when the rules themselves were being written. And from that chaos, somehow, order emerged, the universe cooled and expanded, and here we are, billions of years later, contemplating that first incomprehensible instant. Cosmic inflation, if it occurred, lasted only a fraction of a second, but it expanded the universe by an enormous factor. perhaps 1026 times or more. This exponential growth smoothed out the universe, stretched it flat, and magnified quantum fluctuations into the seeds of galaxies. Inflation also explains why the universe appears so uniform. Regions that are now far apart were once close enough to reach thermal equilibrium before inflation flung them across the cosmos. Some versions of inflation suggest it may be eternal, with different regions stopping inflation at different times, each becoming a separate universe in a multiverse. These ideas push the boundaries of science, blending cosmology with quantum mechanics and philosophy. They may be difficult or impossible to test directly, but they inspire us to think beyond the observable, to imagine possibilities vaster than anything we've known. And tonight, as you drift toward sleep, you can let these vast possibilities carry you, knowing that the universe is stranger and more wonderful than we've yet discovered. Dark energy remains one of the deepest mysteries in cosmology. We know it exists because we observe the universe's accelerating expansion, but we don't know what it is. One possibility is that dark energy is the cosmological constant, a property of space itself, an energy inherent to the vacuum. Einstein originally introduced the cosmological constant to keep the universe static, then abandoned it when Hubble discovered expansion. But observations of distant supernovae revived it, suggesting that empty space has energy, and as the universe expands, more space means more dark energy, pushing expansion faster. Another possibility is that dark energy is a dynamic field, something that changes over time, called quintessence. We don't yet know which, if either, is correct. What we do know is that dark energy will shape the universe's ultimate fate, and understanding it is one of the great quests of modern cosmology. For now, it remains a gentle mystery, a force pushing the cosmos outward, slowly and inexorably, like a breath that never ends. If dark energy continues to dominate, the universe's expansion will accelerate forever. Galaxies beyond our local group will recede faster and faster, eventually moving so quickly that their light will never reach us. The night sky will grow emptier over trillions of years, as distant galaxies disappear beyond the cosmic horizon. Eventually, star formation will cease as galaxies exhaust their gas. Existing stars will burn out, one by one, leaving behind white dwarfs, neutron stars, and black holes. The universe will enter an era called the degenerate era, lit only by the faint glow of dying embers. Later still, even black holes will evaporate through Hawking radiation, a quantum process that slowly returns their mass to space as faint particles. In the end, the universe may become a cold, dark, nearly empty expanse, close to absolute zero, with only the faintest whispers of energy remaining. This end, called heat death, is incomprehensibly far in the future, perhaps 100 years or more. It's a peaceful ending in a way, the universe settling into its final rest, having exhausted all its possibilities. But the future is uncertain, and other scenarios are possible. If dark energy changes over time, or if some other process intervenes, the universe's fate could be different. In one scenario, called the Big Rip, dark energy grows stronger, accelerating expansion so violently that eventually even atoms are torn apart. In another, the Big Crunch, expansion halts and reverses, gravity pulling everything back together in a cosmic collapse, perhaps to be reborn in a new Big Bang. There's even speculation about cyclic models, where the universe goes through endless cycles of expansion and contraction, each cycle creating a new cosmos from the ashes of the old. We don't know which, if any, of these will occur. The universe's ultimate fate is still an open question, a mystery waiting trillions of years to unfold. But tonight, here and now, the universe is alive, full of stars and galaxies, and you are part of it, alive and aware, experiencing this brief, precious moment of cosmic history. The Big Bang was not an explosion in space, but an expansion of space itself, including time. This means asking what happened before the Big Bang may not make sense. There was no before because time itself began with the Big Bang. This is a difficult concept to grasp because our intuition is built on cause and effect, on one moment following another. But if time itself had a beginning, then the universe is, in a sense, self-contained without a cause in the usual sense. Some cosmologists explore models where the Big Bang was not the absolute beginning, but a transition from some earlier state, perhaps a previous universe collapsing, or a quantum fluctuation in a timeless void. These ideas are speculative and push the limits of science and philosophy, but they remind us that the universe challenges our assumptions, invites us to think beyond common experience, and rewards curiosity with wonder. And as you rest tonight, you can let go of the need to understand everything completely. Mystery is part of the beauty. Cosmic rays are high-energy particles, mostly protons, that travel through space at nearly the speed of light. They originate from supernovae, pulsars, black holes, and other violent cosmic events, and they bombard Earth constantly, though our atmosphere shields us from most of them. Some cosmic rays have energies so high that scientists aren't sure what could accelerate them. They're among the most energetic particles in the universe. When a cosmic ray strikes Earth's atmosphere, it collides with air molecules, creating a shower of secondary particles that rain down to the surface. Detectors on the ground can observe these showers and trace them back to their origins. Cosmic rays are messengers from the most extreme environments in the cosmos, carrying information from exploded stars and distant galaxies. Right now, as you lie here, cosmic rays are passing through the atmosphere, through your roof, through your body. Invisible, mostly harmless, a gentle reminder that you're connected to the wider universe, part of a vast, interconnected web of matter and energy. Galaxies can collide and merge, and when they do, they don't destroy each other. They create something new. The gravitational interaction during a collision can trigger bursts of star formation as gas clouds are compressed, lighting up the galaxies with brilliant young stars. Over millions of years, the galaxies spiral around each other, losing energy through gravitational radiation and friction, eventually merging into a single, larger galaxy. The supermassive black holes at each galaxy's center also spiral inward and may eventually merge, releasing gravitational waves. These collisions are slow and graceful on cosmic timescales, violent only in the sense that they reshape galaxies entirely. Hubble and other telescopes have captured beautiful images of colliding galaxies, their shapes distorted, stretched into tails and bridges of stars. These images remind us that even galaxies are not permanent, that transformation is built into the cosmos, and that endings and beginnings are often the same event, seen from different perspectives. Take a moment to notice your breathing. Don't change it, just observe it. The gentle rise and fall of your chest, the cool air coming in, the warm air going out. You're doing perfectly. The universe doesn't ask you to understand it all tonight. It's enough to simply rest here, letting these ideas float around you like distant stars, beautiful and untouchable. If you feel sleepy, welcome it. If your thoughts wander, that's fine too. You're exactly where you need to be. Let the weight of the day dissolve, let the cosmos hold you gently, and know that you're safe. Gravitational waves are ripples in the fabric of spacetime itself, caused by the acceleration of massive objects. When two black holes orbit each other and spiral inward, or when neutron stars collide, they release energy as gravitational waves that spread outward at the speed of light, stretching and squeezing space as they pass. These waves are incredibly weak by the time they reach Earth. Detectors like LIGO and Virgo measure changes in distance smaller than a fraction of the width of a proton. Yet we can detect them, and in doing so, we hear the universe in a new way. Gravitational waves carry information that light cannot, allowing us to observe events hidden from traditional telescopes. The first detection in 2015 confirmed Einstein's century-old prediction and opened a new era of astronomy. It's as if the universe has been speaking all along and we've finally learned to listen. These waves pass through us constantly, unnoticed, a gentle vibration of space-time, a whisper from distant cosmic events. The James Webb Space Telescope, launched in 2021, is the most powerful space telescope ever built, designed to observe the universe in infrared light. Infrared passes through dust clouds that block visible light, allowing Webb to see into stellar nurseries where stars are being born, and to peer back in time to observe the first galaxies that formed after the Big Bang. Webb's images are breathtaking. Galaxies stretched and magnified by gravitational lensing, exoplanet atmospheres analyzed in unprecedented detail, and deep fields showing thousands of galaxies in a patch of sky no bigger than a grain of sand held at arm's length. Each image is a reminder of how much we've learned and how much more there is to discover. Webb is giving us baby pictures of galaxies, glimpses of the universe when it was only a few 100 million years old, still forming its first structures. These observations are rewriting textbooks, challenging theories, and filling astronomers with wonder. The cosmos is revealing itself, layer by layer, and we're privileged to witness it. Exoplanets are planets orbiting stars other than the Sun, and we've discovered thousands of them in the past few decades. They come in astonishing variety. Hot Jupiters orbiting close to their stars, super-Earths larger than our planet but smaller than Neptune, icy worlds, rocky worlds, and even planets orbiting binary stars. Some exoplanets lie in the habitable zone, the region around a star where liquid water could exist on a planet's surface. Finding liquid water doesn't guarantee life, but it's a promising sign. Astronomers are now beginning to study exoplanet atmospheres, searching for biosignatures, chemical signs that might indicate life, like oxygen or methane in specific combinations. We don't yet know if we're alone in the universe, but every exoplanet discovered is a new possibility, a new place where life might exist or have existed. The universe may be teeming with life, or we may be rare. Either way, the search continues, patient and hopeful, and every answer brings new questions. The Drake equation is a formula that estimates the number of active, communicative extraterrestrial civilizations in our galaxy. It multiplies together factors like the rate of star formation, the fraction of stars with planets, the number of planets that could support life, the fraction where life actually arises, the fraction where intelligent life develops, the fraction that develops technology, and how long such civilizations last. The equation doesn't give us a definitive answer because many of these factors are uncertain, but it provides a framework for thinking about the question. Some solutions suggest thousands of civilizations, others suggest we might be alone. The Fermi paradox asks, if civilizations are common, where is everyone? Why haven't we detected any signals? Perhaps civilizations are rare or short-lived, or they don't use technologies we can detect. Or perhaps they're out there, listening just as we are, waiting quietly in the cosmic silence. The universe is vast enough to hold many answers, and the question itself is a kind of companionship, wondering together about who else might be out there under distant stars. The Voyager spacecraft, launched in 1977, have traveled farther than any human-made objects, now beyond the influence of the sun's solar wind, drifting in interstellar space. Each carries a golden record, a message from Earth, a collection of sounds, music, and images representing humanity. The records are meant for any intelligent beings who might find them, though the chances are vanishingly small. Voyager will drift for millions of years, long after Earth and the Sun are gone, silent ambassadors carrying greetings across the void. There's something poignant about this, a message in a bottle cast into the ocean of space, more symbolic than practical. It's a gesture of hope, a declaration that we were here, that we wondered and explored and reached out, even knowing we might never receive an answer. The golden record is humanity at its best, curious, creative, hopeful, and it will outlast all of us. A whisper carried on the solar wind into the great silence of the cosmos. The observable universe contains an estimated 2 trillion galaxies, each with millions or billions of stars and countless planets. The numbers are so large they lose meaning, yet each galaxy is a real place, filled with light and gravity, dust and time. If you could visit one galaxy per second, it would take you over 63,000 years just to visit them all once. And these are only the galaxies we can see. The universe beyond our horizon may be even larger, perhaps infinite. In the face of such vastness, it's easy to feel small. But you can also feel wonder, awe, and a kind of belonging. You are made of the same atoms forged in stars, governed by the same laws of physics, part of the same unfolding story. The universe is not something separate from you. It's the context in which you exist, the stage on which your life plays out. And tonight, as you drift toward sleep, you can rest in that vastness, held gently by the same forces that hold galaxies together, safe in the knowledge that you belong here, in this vast, beautiful cosmos. The Hubble ultradeep field is one of the most famous images in astronomy, a photograph of a tiny patch of sky, about 1/13 the diameter of the full moon, taken by the Hubble Space Telescope over several months. That tiny patch contains about 10,000 galaxies, each one a city of stars, some close, some so distant their light has traveled for over 13 billion years. Almost every point of light in the image is a galaxy, not a star. The image is a humbling reminder of the universe's scale. If that's what's in one tiny patch, imagine the entire sky. And beyond what we can see, there may be more, endlessly more. The ultra-deep field invites us to imagine the stories in each of those galaxies, the stars being born and dying, the planets orbiting, perhaps life arising, civilizations wondering if they're alone. It's an image of possibility, of connection across incomprehensible distances, a portrait of the universe's depth and richness. And it was captured by a telescope orbiting Earth, a tool built by curious beings on a small blue planet, reaching out to understand their place in the cosmos. Time dilation is a consequence of Einstein's theory of relativity, which tells us that time is not absolute. It passes at different rates depending on speed and gravity. If you were to travel at speeds close to the speed of light, time would pass more slowly for you than for someone at rest. Similarly, time passes more slowly in strong gravitational fields. An astronaut orbiting Earth ages slightly slower than people on the surface, though the difference is minuscule, only fractions of a second over months. Near a black hole's event horizon, time dilation becomes extreme. An outside observer would see someone falling toward the black hole appear to slow down and freeze, while the falling person would experience time normally, crossing the horizon in finite time. This strange, counterintuitive behavior is real and has been confirmed by experiments. It reminds us that time is not the rigid framework we imagine, but a flexible part of the universe, woven together with space into space-time, bending and stretching according to the matter and energy it contains. The concept of the cosmological horizon is fascinating and a little melancholy, because the universe is expanding, and because light has a finite speed, there's a limit to how far we can see. More than that, as the universe expands faster and faster due to dark energy, galaxies beyond a certain distance are receding from us faster than light can travel through the expanding space between us. This means we will never see light from those galaxies. They are beyond our cosmological horizon, forever hidden. And as time goes on, more and more galaxies will cross that horizon, disappearing from view. Future astronomers, trillions of years from now, might see a much emptier universe, only the galaxies in their local cluster remaining, with no evidence of the wider cosmos. They might never know the universe is expanding, or that there's anything beyond their little island of stars. It's a reminder of how fortunate we are to live now, when the universe is still rich and visible, full of light and story, and we can look out and see deep into space and time. Cosmic strings are hypothetical one-dimensional defects in space-time, incredibly thin but with immense mass, remnants from the very early universe. If they exist, they would be thinner than an atom but stretch across vast distances, perhaps across entire galaxies, and their gravity would be so strong they could bend light passing nearby. Cosmic strings are predicted by some theories of the early universe, forming when the cosmos cooled and underwent phase transitions, like cracks forming in ice. They're purely theoretical, no one has detected one. But if they exist, they could have influenced the formation of large-scale structures, seeding the cosmic web. They would be relics from an era we can barely imagine, fossils of the universe's infancy, hidden in the fabric of space itself. Even if we never find them, the idea is beautiful. Invisible threads woven through the cosmos, connecting past and present, a reminder that the universe may hold wonders we've only begun to dream of. The heat-death scenario, the universe's eventual cold, dark end, sounds bleak, but it's so far in the future that it's almost abstract. The sun will burn out in about 5 billion years, long before the universe grows cold. Earth's oceans will evaporate and the planet will become uninhabitable. But the universe itself will continue, stars still shining, galaxies still colliding, for trillions of years beyond that. And even after the last star dies, black holes will persist for incomprehensible eons before evaporating. The universe's timeline is so vast that humanity's entire history, all of recorded time, is less than a blink. And in that blink, we've built civilizations, created art, explored space, and wondered about our place in the cosmos. The universe's end, if it comes, is no reason for despair. It's a reminder to appreciate the now, the brief window of warmth and light and life. You are here, in a time when stars shine and galaxies dance, and that is enough. Tonight, let the distant future rest where it is, distant and uncertain, and bring your attention back to this moment, this breath, this peaceful rest. White dwarfs are the remnants of stars like our sun, the final stage after a star has shed its outer layers and exhausted its fuel. A white dwarf is incredibly dense, about the mass of the sun compressed into something the size of Earth. With no fusion to produce new energy, a white dwarf simply radiates away its stored heat, slowly cooling over billions of years. Eventually, it will become a black dwarf, a cold, dark cinder, though the universe isn't old enough for any black dwarfs to exist yet. White dwarfs can have exotic properties. Some are made of crystallized carbon and oxygen, essentially giant cosmic diamonds. Others, in binary systems, can accrete matter from a companion star, occasionally flaring up in a nova. White dwarfs are peaceful endings, quiet epilogues to stellar lives, fading slowly into darkness. They remind us that endings are not always violent, that some things simply dim and rest, and there's a gentle dignity in that. Supernovae come in different types, each with its own cause and characteristics. Type Ia supernovae occur in binary systems where a white dwarf accumulates matter from a companion star until it reaches a critical mass, about 1.4 times the Sun's mass. At that point, carbon fusion ignites explosively throughout the star, obliterating it entirely. Type Ia supernovae are remarkably consistent in brightness, which makes them useful as standard candles for measuring cosmic distances. It was observations of distant Type Ia supernovae that revealed the universe's accelerating expansion and led to the discovery of dark energy. Other supernovae, types II, Ib, and Ike, result from massive stars collapsing at the end of their lives. These explosions scatter heavy elements into space, enriching the interstellar medium with the raw materials for new stars and planets. Supernovae are both death and birth, endings that seed beginnings, destruction that creates. They're essential to the universe's chemical evolution, and without them there would be no planets like Earth, no life, no you. Even in their violence, they're nurturing, generous, giving back to the cosmos. The anthropic principle suggests that the universe appears fine-tuned for life because, if it weren't, we wouldn't be here to observe it. The fundamental constants of physics, the strength of gravity, the mass of the electron, the speed of light, seem exquisitely balanced to allow for stars, planets, and chemistry. If any of these constants were even slightly different, the universe might be lifeless, stars might not form, atoms might not be stable, complexity might never arise. This fine-tuning is puzzling. One explanation is the multiverse. If there are countless universes with different constants, we naturally find ourselves in one where the constants allow life. Another view is that we're simply lucky, or that there's a deeper principle we haven't discovered yet. The anthropic principle is less a solution than a way of framing the question. It reminds us that our existence is improbable and precious, that we live in a cosmos where the conditions are just right, and that awareness itself is a kind of cosmic gift, a universe waking up to contemplate itself. The Oort cloud is a vast, spherical shell of icy objects surrounding our solar system, extending perhaps halfway to the nearest star. It's the source of long-period comets, those visitors that swing through the inner solar system once every few thousand or million years. The Oort cloud is so distant and diffuse that we've never directly observed it. We infer its existence from the comets it sends our way. These icy bodies are remnants from the solar system's formation, leftovers flung outward by the gravity of the giant planets. They've been sitting in cold storage for billions of years, frozen and unchanged, until a passing star or gravitational perturbation nudges one inward. Then it falls toward the sun, heating and developing a glowing tail, becoming a comet. Comets are messengers from the solar system's edge, carrying pristine material from the early solar system. They're beautiful and ephemeral, visitors from the dark, reminding us that even in the emptiness beyond the planets, there's structure, history, and the potential for wonder. The Sun is an ordinary star, one of about 100 billion in the Milky Way, and the Milky Way is one of 2 trillion galaxies in the observable universe. By some estimates, there are more stars in the universe than grains of sand on all Earth's beaches. Each of those stars might have planets, and each planet is a world with its own story, its own skies, its own potential. The sheer scale is overwhelming, and yet each individual object, each star, planet, moon, is unique. No 2 stars are exactly alike, no 2 planets identical. The universe is both repetitive and endlessly creative, following the same physical laws everywhere, yet producing infinite variation. This duality is echoed in your own existence. You're made of common elements, governed by the same biology as every human who's ever lived, yet you're unique, irreplaceable. The universe makes multitudes, and among those multitudes it made you. There's comfort in that, being both ordinary and extraordinary, one among countless, yet singular. The Sun produces energy through nuclear fusion, converting about 600 million tons of hydrogen into helium every second, releasing energy according to Einstein's equation E equals mc2. The mass lost in this process becomes energy, powering the Sun's light and heat. This has been happening for 4.6 billion years, and it will continue for another 5 billion, with remarkable stability. The Sun is in a phase called the main sequence, where fusion in the core balances gravity's inward pull, keeping the star stable. Eventually, the Sun will exhaust its core hydrogen and begin fusing helium, swelling into a red giant and engulfing the inner planets, possibly including Earth. But that's billions of years away, so far in the future that it's almost meaningless on human timescales. For now, and for countless generations to come, the Sun will rise each morning, steady and warm, a constant presence. It's a reminder that while the universe operates on vast timescales, it also provides stability, pockets of peace and predictability where life can flourish. Tonight, rest easy knowing the Sun will rise again, and the cosmos will continue its slow, patient dance. Black holes are not eternal. Stephen Hawking predicted that they slowly evaporate through a process called Hawking radiation, a quantum effect near the event horizon. Particle-antiparticle pairs constantly form in empty space, and near a black hole, one particle can fall in while the other escapes, carrying away a tiny bit of the black hole's mass. Over unimaginable timescales, far longer than the current age of the universe, a black hole will lose all its mass and disappear in a final burst of radiation. Smaller black holes evaporate faster than large ones, and stellar mass black holes will take about 1067 years to evaporate. Supermassive black holes will take even longer. The universe will have long since grown cold and empty before the last black holes vanish. But the fact that they do evaporate is profound. It means even the most enduring objects are temporary. Nothing lasts forever, not stars, not galaxies, not even black holes. Everything changes, everything passes, and there's a strange peace in accepting that impermanence is woven into the fabric of existence. You're doing so well. Let your body feel heavy, supported completely by whatever you're resting on. There's no effort needed here, no trying. Just let yourself be held by gravity, that gentle force that keeps you grounded. The same force that holds planets in orbit and galaxies together. You're part of something vast and ancient, and right now, all you need to do is breathe and rest. If your mind is still active, that's okay. Let thoughts come and go like clouds drifting across a sky. You don't need to hold on to them. Let the universe hold you instead, and trust that sleep will come when it's ready. The concept of spacetime is central to modern cosmology. Before Einstein, space and time were thought of as separate, space as a static stage, and time as a universal clock ticking the same for everyone. Einstein's relativity showed that space and time are woven together into a single four-dimensional fabric called spacetime. Events happen not just where and when, but in a combined location in space-time. Mass and energy curve space-time, and objects follow the straightest paths through those curves, which we perceive as gravity. This means gravity isn't a force pulling you down, but the result of Earth curving space-time around it, and you following that curve. Space-time is dynamic, flexible, responding to matter and energy. It's a beautiful unification, showing that the universe is more interconnected than we imagined. And as you lie here, you're not just resting in space, you're resting in space-time, part of a four-dimensional tapestry stretching from the Big Bang to the distant future. Light has a dual nature. It behaves as both a wave and a particle, depending on how you observe it. As a wave, light has wavelength and frequency, and it can interfere with itself, creating patterns of bright and dark. As a particle, it comes in discrete packets called photons, each carrying a specific amount of energy. This wave-particle duality was one of the first hints of quantum mechanics, and it remains one of the most beautiful mysteries in physics. It's not that light is sometimes a wave and sometimes a particle. It's always both, and the universe reveals different aspects depending on what questions we ask. This duality is echoed throughout quantum mechanics, a reminder that reality is richer and stranger than our everyday intuition. Light connects us to the cosmos. The photons entering your eyes from the stars left those stars years, centuries, or millennia ago, traveling across space to meet you. Every glance at the night sky is a connection across time, a conversation with the past, whispered in the language of light. The Fermi Gamma Ray Space Telescope detects gamma rays, the highest energy form of light, emitted by the universe's most violent and energetic events, supernova explosions, colliding neutron stars, matter falling into black holes and pulsars. Gamma rays can't penetrate Earth's atmosphere, so they must be observed from space. When Fermi detects a gamma ray burst, it alerts astronomers, who turn other telescopes toward the source. These bursts are fleeting, lasting seconds to minutes, but releasing as much energy as the sun will in its entire lifetime. They are among the brightest explosions in the universe, visible across billions of light years. Gamma-ray astronomy opens a new window on the universe, revealing phenomena invisible to optical telescopes. Each burst is a cosmic laboratory, where matter and energy behave in extreme ways we can barely recreate on Earth. And each detection is a reminder that the universe is constantly active, energetic, full of events unfolding at every moment. A living cosmos even when the night sky appears silent and still. Gravitational lensing occurs when a massive object, like a galaxy or cluster, bends the path of light from a more distant object, acting like a cosmic magnifying glass. The effect can create multiple images of the background object, or stretch it into arcs and rings, called Einstein rings. Astronomers use gravitational lensing to study distant galaxies that would otherwise be too faint to see, and to map the distribution of dark matter in clusters. Some of the most stunning images from Hubble and Webb show lensing in action, distorted, magnified galaxies wrapped around massive foreground clusters. Lensing is a powerful tool, allowing us to see farther and learn more than we could with light alone. It's also a beautiful demonstration of general relativity in action, showing how mass curves space and bends light, turning the universe itself into a telescope. The cosmos helps us see deeper into itself, as if it wants to be understood, revealing its secrets to those patient enough to look carefully. The scale of the universe can be difficult to grasp, so let's take a journey. Imagine shrinking the sun to the size of a basketball. On that scale, Earth would be a tiny bead about the size of a peppercorn, orbiting about 30 meters away. Jupiter would be a small marble about 150 meters away, and Neptune, the outermost planet, would be nearly a kilometer away. The nearest star, Proxima Centauri, would be about 8,000 kilometers away, roughly the distance from New York to Beijing. The Milky Way galaxy would be about 25 million kilometers across, and Andromeda, the nearest large galaxy, about 650 million kilometers away. On this scale, the observable universe would be about 2.4 trillion kilometers in diameter. These numbers lose meaning, but the point is clear. The universe is vast beyond comprehension, and we're a tiny part of it. Yet that tiny part is aware, capable of wonder, able to imagine those distances and understand, at least in part, the cosmos we inhabit. Scale doesn't diminish significance. It enhances the miracle of consciousness existing at all. Neutrinos are ghostly particles, nearly massless, that interact so weakly with matter they can pass through entire planets without being stopped. They're produced in nuclear reactions, including those in the Sun's core and in supernovae. Trillions of neutrinos from the Sun pass through your body every second, day and night, without you noticing. Detecting neutrinos requires massive underground detectors filled with water or other materials, watching for the rare occasions when a neutrino interacts with an atom and produces a flash of light. Neutrino astronomy is still young, but it's already revealed important information. Neutrinos from supernova 1987 A arrived at Earth hours before the light, carrying news of the explosion from deep within the dying star. Neutrinos let us see inside the Sun, confirming our models of how fusion works. They're messengers from realms light cannot reach, and they remind us that the universe is full of invisible phenomena, whole layers of reality we're only beginning to perceive. Astronomy is one of the oldest sciences, and humans have been watching the skies for tens of thousands of years. Ancient peoples tracked the moon's phases, the sun's path, the motions of planets, and the patterns of stars. They built monuments aligned with solstices and equinoxes, created calendars, and wove the stars into their myths and stories. Astronomy and cosmology have always been intertwined with human culture, philosophy, and religion. The questions we ask about the universe, where did it come from, how will it end, are we alone, are deeply human questions, as much about meaning as about mechanics. Every civilization that has looked up at the night sky has wondered, and each has found its own answers. Today, we have telescopes and satellites, equations and observations, but the sense of wonder remains the same. The stars that guided ancient travelers are the same stars you can see tonight, and the questions they inspire are timeless. You're part of that long tradition, lying here under the same cosmos that has inspired countless generations, connected across time by shared curiosity and awe. The Milky Way galaxy is about 100,000 light-years across, a barred spiral with a bright central bulge and graceful arms winding outward. Our solar system is located in a minor arm called the Orion Spur, about 26,000 light-years from the galactic center. We orbit the galaxy's center at about 230 kilometers per second, completing one orbit every 225 million years, a galactic year. In the time since dinosaurs walked the Earth, the solar system has completed less than one full orbit. The Milky Way is home to hundreds of billions of stars, and we're only just beginning to explore its structure and contents. When you look up at the Milky Way's band of light stretching across the sky, you're seeing the combined glow of countless stars in the galactic disk, too far and numerous to see individually. That band is your home galaxy seen from inside, a river of light reminding you that you're part of something ancient, vast, and beautiful. Every star in that band has its own story, and together they form the community of the Milky Way, bound by gravity, spinning through space. Dark matter, that mysterious 27% of the universe, may be made of particles we've never detected, sometimes called WIMPs, weakly interacting massive particles. Despite decades of searching, we've never directly detected dark matter particles, though we continue to build more sensitive detectors deep underground, shielded from cosmic rays and other interference. Another candidate is axions, hypothetical particles much lighter than WIMPs. Or dark matter might be something else entirely, something we haven't imagined yet. The search for dark matter is one of the great detective stories in physics, a hunt for an invisible suspect whose effects are everywhere but whose identity remains unknown. It's humbling and exciting. There's a major component of the universe we don't understand, and solving that mystery could revolutionize physics. But even without knowing what dark matter is, we can see its effects, mapping its distribution, learning how it shapes galaxies. The universe is generous with its clues, even when it withholds final answers. The local group, our small corner of the universe, includes the Milky Way, Andromeda, and over 50 smaller galaxies, bound together by gravity. Many of the smaller galaxies are dwarf galaxies, some with only a few million stars, orbiting the Milky Way and Andromeda like satellites. These dwarf galaxies are laboratories for studying dark matter, because they're thought to contain far more dark matter than ordinary matter. The local group is about 10 million light-years across, a cozy neighborhood by cosmic standards. Beyond the local group, the next significant structure is the Virgo cluster, about 54 million light-years away, containing over 1,000 galaxies. The local group itself is being pulled toward Virgo by gravity, drifting through space at hundreds of kilometers per second. You're not just on a planet orbiting a star, but in a star system orbiting a galaxy, in a galaxy moving through a group, in a group falling toward a cluster. Motion within motion, wheels within wheels, and yet from here on this bed, everything seems still and peaceful. That's the beauty of perspective. You can zoom out to cosmic scales or zoom in to this quiet moment, and both are equally real. Pulsars, those rapidly spinning neutron stars, were first discovered in 1967 by Jocelyn Bell Burnell. She noticed regular pulses of radio waves, so precise they were initially nicknamed LGM for little green men, half-jokingly suggesting they might be alien signals. But they turned out to be natural, neutron stars spinning at incredible speeds, beaming radiation like lighthouses. Some pulsars spin hundreds of times per second, and their timing is so stable they rival atomic clocks. Astronomers use pulsars as tools. Timing irregularities can reveal the presence of orbiting planets or companion stars, and patterns in many pulsars can help detect gravitational waves from the early universe. Pulsars are gifts to astronomers, natural laboratories for extreme physics, and lighthouses in the dark. Their regular pulses a steady reminder that even in the chaos of stellar death, there can be order, rhythm, and reliability. Their discovery was accidental, a reminder that the universe holds surprises, And sometimes the most important discoveries come from noticing something unexpected. Cosmic inflation, that exponential expansion in the first fraction of a second, may have left imprints on the cosmic microwave background, specific patterns in polarization called B modes. Detecting these would be powerful evidence for inflation, showing the universe's quantum fluctuations magnified to cosmic scales. Scientists have searched for these signals using telescopes in Antarctica and space, and while there have been hints, definitive detection remains elusive. The challenge is separating the signal from foreground noise like dust in our own galaxy. But the search continues, patient and meticulous, because finding B modes would be a profound confirmation of inflation, a glimpse of quantum gravity, and a window into the universe's first moments. This is how science works, asking precise questions, building instruments to answer them, and accepting that some answers take decades or longer to find. The universe doesn't reveal its secrets quickly, but it does reveal them to those who persist, who look carefully, who listen with patience and care. Kepler's laws of planetary motion, discovered over 400 years ago, describe how planets orbit the Sun. Elliptical orbits, with the Sun at one focus, sweeping out equal areas in equal times and orbital periods related to distance. These laws, derived from careful observation, were later explained by Newton's law of gravity, and later still by Einstein's general relativity. The progression from observation to explanation to deeper explanation is a beautiful example of how science builds on itself, each generation standing on the shoulders of the previous, seeing a little farther. Those same laws govern exoplanets orbiting distant stars, moons orbiting planets, even binary stars orbiting each other. Gravity is universal, and the mathematics that describe it work everywhere, from the smallest satellite to the largest galaxy cluster. There's a deep unity in the cosmos, a set of rules that apply without exception, and discovering those rules is one of humanity's greatest achievements. As you rest tonight, you can trust in that order, in the predictable, reliable laws that keep planets in their orbits and you safely on Earth. The Kuiper Belt is a region beyond Neptune, filled with small icy bodies, remnants from the solar system's formation. Pluto is the most famous Kuiper Belt object, but there are thousands of others, ranging from tiny to Pluto-sized. The Kuiper Belt is like the asteroid belt, but farther out and much larger, a disk of leftovers that never coalesced into a planet. Some Kuiper Belt objects have highly elliptical orbits, occasionally bringing them closer to the Sun, where they can develop tails and become short-period comets. Studying the Kuiper Belt helps us understand how the solar system formed, what materials were present in the outer regions, and how planetary systems evolve. It's a frontier of exploration. NASA's New Horizons spacecraft flew past Pluto in 2015 and then visited another Kuiper Belt object, Arrokoth, giving us our first close-up views of these distant worlds. The Kuiper Belt reminds us that the solar system doesn't end at Neptune, that there's still so much to explore and discover, even in our own cosmic backyard. The Moon, Earth's companion, has been a source of wonder and inspiration for all of human history. It's unusually large for a moon, about a quarter the diameter of Earth, and it's thought to have formed from debris after a Mars-sized object collided with the young Earth billions of years ago. The Moon stabilizes Earth's axial tilt, which helps moderate our climate and seasons. It's tidally locked, always showing the same face to Earth, because its rotation period matches its orbital period. The far side of the Moon, sometimes incorrectly called the dark side, is hidden from Earth, but it's not dark. It receives just as much sunlight as the near side. The Moon's surface is ancient, scarred by billions of years of impacts, and walking on it feels like walking through history. 12 humans have walked on the Moon between 1969 and 1972, an astonishing achievement that showed what humanity can accomplish. Looking up at the Moon tonight, you're looking at a world that people have visited, left footprints on, and returned from. A reminder that the cosmos is not just a place to observe, but to explore. The speed of light is not just a speed limit for matter. It's also the speed at which information, causality, and changes in fields propagate. If the sun suddenly disappeared, Earth wouldn't feel the gravitational change for about 8 minutes, the same time it takes light to travel from sun to Earth. Gravity, like light, travels at the speed of light in the form of gravitational waves. This means there's a fundamental horizon to how quickly things can interact in the universe. No signal, no influence can move faster than light. This limit shapes the structure of spacetime, ensuring causality, cause precedes effect, and preventing paradoxes. It's a deep, fundamental feature of the universe, woven into the equations of relativity. And while it means we can never travel to distant stars quickly, it also means the universe has structure, order, and predictability. The speed of light is not a frustrating barrier, but a gentle rule that keeps the cosmos coherent and comprehensible. Stellar nurseries like the Eagle Nebula, pillars of creation, are regions where new stars are being born. These pillars are vast columns of gas and dust, sculpted by the radiation from nearby young stars. Inside the densest parts, gravity pulls material together, forming protostars. Over millions of years, these protostars gather mass, heat up, and eventually ignite fusion, becoming stars. The pillars of creation are beautiful and iconic, captured by Hubble in stunning detail. They're about 7 light-years tall, and they're slowly being eroded by the very stars they're creating. Eventually, the pillars will be destroyed, the gas dispersed, but the stars born there will continue to shine for billions of years. It's a reminder that creation often involves destruction, that birth and death are intertwined, and that the universe recycles itself endlessly, turning old material into new stars, planets, and possibilities. These nurseries are active, dynamic, full of potential, and they remind us that the universe is still creating, still evolving, still young in spirit. The anthropic principle comes in strong and weak forms. The weak form simply observes that we find ourselves in a universe compatible with our existence, which is unsurprising. If it weren't, we wouldn't be here to notice. The strong form suggests the universe must have properties that allow observers to exist at some point, which borders on philosophical or even theological territory. Some scientists are uncomfortable with anthropic reasoning, feeling it's unscientific to invoke our existence as an explanation. Others see it as a valid way to make sense of the universe's apparent fine-tuning, especially in the context of a multiverse. The debate continues, blending physics, philosophy, and metaphysics. But regardless of where you stand, the fact remains. The universe is capable of producing life, consciousness, and observers who can ask why. That capability is built into the fabric of reality, and whether by chance, necessity, or design, it resulted in you lying here tonight thinking about the cosmos. And that's something worth appreciating, whatever the explanation. Let your jaw relax. Often we hold tension there without realizing. Let your tongue rest gently in your mouth and soften the space behind your eyes. Feel how your body is supported, held safely. There's nowhere you need to go, nothing you need to do. The universe is vast and you are small, and that's okay. You're allowed to rest, to let go, to simply be. If you're still awake, that's fine, there's no pressure. But if sleep is starting to pull at you, welcome it. Let yourself drift like a leaf on a gentle stream, carried softly into dreams. The speed of light in a vacuum is constant. Always 299,792,458 meters per second. No matter how fast you're moving, or how fast the light source is moving. This constancy was a puzzle before Einstein, because it seems to violate common sense. If you're moving toward a light source, shouldn't the light reach you faster? But experiments showed it doesn't. Einstein resolved this by realizing that space and time themselves must adjust, contracting and dilating, to keep the speed of light constant for all observers. This leads to relativity's strange predictions: time dilation, length contraction, the relativity of simultaneity. These aren't illusions, they're real features of spacetime. The constancy of light speed is a cornerstone of modern physics, and it's been tested countless times, always confirmed. It's one of the universe's fundamental rules, elegant and unyielding, a constant in a changing cosmos, something you can always rely on. Photons, the particles of light, are massless, which is why they can travel at the speed of light. Anything with mass would require infinite energy to reach light speed, but photons are born traveling at that speed and never slow down in a vacuum. They carry energy and momentum, and they're affected by gravity, not because gravity pulls on their non-existent mass, but because gravity curves spacetime, and photons follow those curves. Photons are also quantum objects, exhibiting wave-particle duality and entanglement. A photon leaving a star thousands of light-years away carries information about that star, traveling through space for millennia until it reaches your eye, where it's absorbed. Its journey ending as a tiny signal in your retina, translated into vision by your brain. That single photon connected you, briefly, to a distant star. Every time you see starlight, you're completing a journey that photon began long ago, a silent conversation across the void. The asteroid belt between Mars and Jupiter is home to millions of rocky bodies ranging from dust grains to Ceres, a dwarf planet about 940 kilometers across. Despite its depiction in movies as a dense field of tumbling rocks, the asteroid belt is mostly empty space. Spacecraft pass through it without difficulty. The asteroids are remnants from the solar system's formation, material that never coalesced into a planet, likely because Jupiter's gravity stirred them up, preventing accretion. Some asteroids are metallic, rich in iron and nickel, possibly the cores of small protoplanets that shattered in collisions. Others are rocky or carbonaceous, Studying asteroids gives us clues about the early solar system's composition and conditions. And some asteroids are potentially hazardous, their orbits bringing them close to Earth, reminding us that space is dynamic and that impacts, though rare, are part of planetary history. But they're also resources. Future missions may mine asteroids for metals and water, turning them from hazards into assets. The concept of infinity appears often in cosmology. The universe may be spatially infinite, stretching forever in all directions. Time may extend infinitely into the future, the universe cooling and expanding forever. Some quantities, like the density at a black hole's singularity, may be infinite, though that likely signals a breakdown of our theories rather than a true infinity. Infinity is difficult for the human mind to grasp. It's not just very large, it's beyond size. In mathematics, infinities come in different sizes, some larger than others, a concept that's both beautiful and bewildering. When we say the universe might be infinite, we're acknowledging the possibility that there's no end, no boundary, no totality we can comprehend. And that's okay. You don't need to understand infinity to appreciate it, to let it wash over you as a reminder of the universe's boundless nature. Tonight, let infinity be a comfort, a sense that the cosmos is endlessly generous, always more to discover, always room for wonder. The search for extraterrestrial intelligence, or SETI, has been ongoing for decades, primarily by listening for radio signals from distant civilizations. Astronomers point large radio telescopes at nearby stars, scanning for patterns that couldn't be natural, repeating sequences, narrow bandwidth signals, anything that suggests technology. So far, we've found nothing definitive, though there have been intriguing signals like the WOW signal in 1977, which has never been explained or repeated. The silence is called the Great Silence, and it's puzzling. Are we alone, or are we simply not listening in the right way or at the right time? Perhaps civilizations are common but short-lived, or they communicate in ways we haven't imagined. SETI continues, patient and hopeful, a search driven more by curiosity than expectation. And even if we never hear a signal, the search itself is meaningful, reaching out, declaring our presence, hoping for a response. It's an act of optimism, a belief that the universe, so vast and full of stars, must hold others like us, wondering if they're alone. Terraforming is the hypothetical process of transforming another planet to make it habitable for humans, most often discussed in the context of Mars. Mars has water ice, a thin atmosphere, and a day length similar to Earth's. With technology, we might thicken its atmosphere, warm it, and perhaps grow plants, gradually making it more Earth-like. This would take centuries or millennia and require resources and effort on a staggering scale. Some see it as humanity's destiny, spreading life throughout the solar system. Others question whether we should, whether altering an entire planet is ethical, especially if there's any native life, even microbial. Terraforming is speculative, a dream more than a plan, but it reflects a deep human impulse to explore, adapt, and make new places home. Whether or not it happens, the idea reminds us that we're capable of thinking on planetary scales, of imagining futures far beyond our lifetimes, and of caring for worlds we'll never see completed. Red giants are stars in the late stages of their lives, having exhausted the hydrogen in their cores. As fusion slows, gravity compresses the core, heating it, while the outer layers expand and cool, giving the star a reddish hue. These stars can be enormous. Betelgeuse, a red supergiant in the constellation Orion, is so large that if it were placed at the Sun's position, it would engulf Mercury, Venus, Earth, and Mars. Red giants are beautiful, glowing softly, nearing the end of their journeys. In about 5 billion years, our Sun will become a red giant, swelling to perhaps Earth's orbit, though by then Earth itself will likely be uninhabitable, its oceans boiled away. The Sun will then shed its outer layers, forming a planetary nebula, leaving behind a white dwarf core. This transformation, while dramatic, is gentle by cosmic standards, taking millions of years. The Sun's red giant phase is a distant future, and in the meantime, it will continue to shine steadily, warming Earth and supporting life, a faithful companion in the sky. Planetary nebulae, despite their name, have nothing to do with planets. They're shells of gas and dust ejected by dying stars like our Sun. As a star becomes a red giant and sheds its outer layers, those layers drift outward, lit from within by the hot core left behind. The result is often stunningly beautiful. Glowing clouds in intricate shapes, rings, bubbles, and jets, colored by different elements emitting light. The Cat's Eye Nebula, the Ring Nebula, the Helix Nebula. These are all planetary nebulae, the final breaths of stars, illuminated tombstones marking where a star once lived. They're relatively short-lived, lasting only tens of thousands of years before dispersing into space, but in that time they are among the most beautiful objects in the sky. They remind us that endings can be beautiful, that even death can create art, and that the matter returned to space will someday form new stars and planets, continuing the cosmic cycle. The Sun's core is an inferno, about 15 million degrees Celsius, where hydrogen nuclei collide with enough energy to overcome their mutual repulsion and fuse into helium. This fusion releases energy, which works its way outward through the Sun's layers, first through the radiative zone, where photons bounce off particles in a random walk that takes thousands of years, then through the convective zone, where hot plasma rises and cooler plasma sinks, and finally to the surface, the photosphere, where the energy escapes as light. The photons you see when you look at the Sun took thousands of years to travel from the core to the surface, but only 8 minutes to travel from the surface to your eyes. In a sense, the sunlight warming your face is ancient, its energy born in the core long ago. The Sun is a patient engine, fusing hydrogen steadily, reliably, giving Earth a stable climate over billions of years, and that stability is part of what makes life possible. The Sun is not just a star, it's our star, and we owe it everything. Seasons on Earth are caused by the tilt of Earth's rotational axis, about 23.5 degrees relative to its orbital plane. This tilt means that as Earth orbits the Sun, different parts of the planet receive more or less direct sunlight at different times of year. When the northern hemisphere is tilted toward the Sun, it's summer there and winter in the southern hemisphere and vice versa. The tilt is thought to have been stabilized by the Moon's gravitational influence, preventing large chaotic swings that could make Earth's climate unstable. Without this tilt, there would be no seasons, just a steady, unchanging pattern of sunlight. Seasons bring variety, change, cycles of growth and rest, and they've shaped life on Earth profoundly. They're a reminder that change is natural, that cycles are part of existence, and that after every winter, spring returns. As you rest tonight, you can trust in those cycles, in the reliability of the Earth's orbit, in the gentle rhythm of seasons that will continue long after this night is over. The Goldilocks zone, or habitable zone, is the range of distances from a star where conditions might be just right for liquid water to exist on a planet's surface. Too close, and water boils away; too far, and it freezes. Earth sits comfortably in the Sun's habitable zone, and astronomers search for exoplanets in similar zones around other stars. Being in the habitable zone doesn't guarantee life. Many other factors matter, like atmosphere, magnetic field, and planetary history. But it's a starting point. Some moons, like Europa and Enceladus, have liquid water beneath icy shells, kept warm by tidal heating, suggesting habitable zones might exist in unexpected places. The concept of habitability is evolving as we learn more, expanding our sense of where life might exist. The universe may have countless habitable worlds, and finding even one with life would transform our understanding of our place in the cosmos. For now, we know of only one habitable world, Earth, our home, precious and rare, deserving of care. Comets, those wanderers from the outer solar system, are sometimes called dirty snowballs, mixtures of ice, rock, and dust. As a comet approaches the Sun, solar radiation heats it, vaporizing ice and releasing gas and dust which stream away in a glowing tail. Comet tails always point away from the Sun, pushed by the solar wind, not trailing behind like you might expect. Comets have been feared and revered throughout history, seen as omens or divine messages. Today, we understand them as natural objects, leftovers from the solar system's formation, carrying pristine material unchanged for billions of years. Missions have visited comets, landing probes on their surfaces, revealing their structure and composition. Comets may have delivered water and organic molecules to early Earth, seeding the planet with the ingredients for life. They're messengers from the solar system's infancy, and their beauty, those long, graceful tails glowing in the night sky, is a reminder that even transient visitors can leave lasting impressions. Supermassive black holes lurk at the centers of most galaxies, including our own Milky Way. They're millions or billions of times more massive than the Sun, yet confined to a region smaller than our solar system. How they grew so large is still a mystery. Did they start as smaller black holes that merged and accumulated matter? Or did they form directly from collapsing gas clouds in the early universe? Observations of distant quasars suggest supermassive black holes existed when the universe was very young, which complicates formation theories. These black holes influence their host galaxies profoundly, regulating star formation through their energetic outflows. When they're actively feeding, they can be the brightest objects in the universe. When quiet, they're invisible, detectable only by their gravitational influence. The one at the center of the Milky Way, Sagittarius A, is remarkably quiet, a sleeping giant. These black holes are both destructive and creative, shaping galaxies, and studying them helps us understand galaxy evolution and the relationship between black holes and the structures they inhabit. Einstein's theory of general relativity has been tested countless times and passed every test with remarkable precision. From the precession of Mercury's orbit to the bending of light by the sun observed during a solar eclipse, to the detection of gravitational waves, relativity's predictions have been confirmed again and again. GPS satellites rely on corrections for both special and general relativity. Time runs slightly faster in orbit than on Earth's surface due to weaker gravity, and slightly slower due to orbital speed. Without these corrections, GPS would drift by kilometers per day. General relativity is more than a theory. It's a tested, reliable description of gravity and spacetime, and it's one of humanity's greatest intellectual achievements. Yet even it has limits. It's incompatible with quantum mechanics at the smallest scales, and we don't yet have a quantum theory of gravity. The search for that theory is ongoing, but for now, relativity guides our understanding of the cosmos, elegant and powerful, a lens through which we see the universe. The concept of entropy, central to thermodynamics, is often described as disorder, but it's more accurately a measure of the number of ways a system can be arranged. High entropy means many possible arrangements. Low entropy means few. The universe began in a very low entropy state, highly ordered, and has been increasing in entropy ever since. Stars burn, galaxies form and evolve, black holes evaporate, all contributing to the universe's gradual slide toward maximum entropy, a state of equilibrium where no energy gradients exist, no work can be done, and nothing interesting happens anymore. This is the heat-death scenario, the universe's thermal equilibrium. But that's incomprehensibly far in the future, and in the meantime there are pockets of low entropy, like Earth, like you, where order and complexity exist temporarily. Life itself is a process that locally decreases entropy, creating structure and organization, though it increases the overall entropy of the surroundings. You are a temporary island of order in the entropic tide, and that makes you precious, a fleeting wonder in a universe trending toward stillness. The formation of the solar system began about 4.6 billion years ago from a rotating cloud of gas and dust, called the solar nebula. Gravity caused the cloud to collapse, and as it did, it spun faster and flattened into a disk. At the center, the protosun formed, growing hotter until fusion ignited. In the disk, dust grains stuck together, forming pebbles, then boulders, then planetesimals, and eventually planets. The inner solar system, closer to the sun, was too hot for volatile materials like water and methane to condense, so the inner planets, Mercury, Venus, Earth, Mars, are rocky. Farther out, beyond the frost line, ice could form, and the outer planets, Jupiter, Saturn, Uranus, Neptune, grew into gas and ice giants, accumulating massive atmospheres. The whole process took tens of millions of years, a blink on cosmic timescales. Our solar system is one of countless such systems throughout the galaxy, each with its own configuration of planets, moons, and minor bodies, each telling a story of formation and evolution. Jupiter, the largest planet in our solar system, has a mass greater than all the other planets combined. It's a gas giant, mostly hydrogen and helium, with no solid surface. Descend into Jupiter, and you'd pass through layers of gas becoming denser and hotter, eventually transitioning to metallic hydrogen under immense pressure. Jupiter's great red spot is a storm larger than Earth, raging for at least 350 years. Jupiter acts as a gravitational shield for the inner solar system, its massive gravity deflecting or capturing comets and asteroids that might otherwise threaten Earth. It has at least 79 moons, including the 4 large Galilean moons, Io, Europa, Ganymede, and Callisto, each a world in its own right. Europa, in particular, has a subsurface ocean beneath its icy shell, making it one of the best candidates for finding extraterrestrial life in our solar system. Jupiter is a giant, a protector, and a system unto itself, a miniature solar system orbiting the Sun, full of mysteries and wonders. Saturn is famous for its stunning rings, made of countless chunks of ice and rock, ranging in size from grains of sand to house-sized boulders. The rings are thin, only about 10 meters thick in most places, but they stretch for hundreds of thousands of kilometers. How they formed is still debated. They may be remnants of a shattered moon or leftover material from Saturn's formation. The rings are not solid. They're a dynamic system with particles orbiting Saturn, shepherded by small moons called shepherd moons that keep the rings confined. Saturn itself is a gas giant, less dense than water with powerful winds and storms. Its largest moon, Titan, has a thick atmosphere and lakes of liquid methane and ethane on its surface, a bizarre, alien landscape. Saturn is a jewel of the solar system, beautiful and serene, and seeing it through a telescope, even a small one, is a breathtaking experience, a reminder of the elegance and variety the cosmos can produce. You've come so far through this journey tonight, and you're doing beautifully. Let go of any need to remember what you've heard. These aren't facts to memorize, just gentle thoughts to carry you towards sleep. Feel the weight of your body, the softness beneath you, the quietness around you. The universe is patient and eternal, and you can rest in that. Let your breathing be slow and natural. Let your thoughts be soft and distant. You're safe, you're calm, and you're exactly where you need to be. Sleep is close now if you want it, and if not, that's okay too. Just rest. Uranus is tilted on its side, its rotational axis nearly parallel to its orbital plane, rolling around the Sun like a ball rather than spinning like a top. This extreme tilt, possibly caused by a massive collision early in its history, gives Uranus unusual seasons. Each pole experiences 42 years of continuous sunlight followed by 42 years of darkness. Uranus is an ice giant, composed mostly of water, methane, and ammonia ices, with a small rocky core. Its atmosphere is bland compared to Jupiter and Saturn, a pale blue-green color due to methane, with fewer visible storms. Uranus has faint rings and 27 known moons, named after characters from Shakespeare and Alexander Pope. It's a distant, mysterious world, visited only once by Voyager 2 in 1986. Uranus reminds us that even within our own solar system, there are strange, alien worlds, places where the familiar rules, like how a planet should spin, are bent or broken. Neptune, the most distant planet from the Sun, is a deep blue world, its color also due to methane in its atmosphere. Despite being farther from the Sun and receiving less energy, Neptune has the fastest winds in the solar system, reaching over 2,000 kilometers per hour. How it generates such powerful winds with so little solar energy is still a mystery. Neptune may have an internal heat source. Its largest moon, Triton, is geologically active, with geysers of nitrogen erupting from its surface. Triton orbits retrograde, opposite to Neptune's rotation, suggesting it was captured from the Kuiper belt rather than forming with Neptune. Neptune was the first planet discovered through mathematical prediction rather than observation. Irregularities in Uranus's orbit suggested another planet, and when astronomers looked where the math predicted, there was Neptune. It's a triumph of human reason, using mathematics to reveal the invisible, and a reminder that the universe follows rules we can decipher. Pluto, demoted from planet to dwarf planet in 2006, remains beloved. It's a small, icy world in the Kuiper belt, with a heart-shaped region of frozen nitrogen called Tombo Regio. New Horizons revealed Pluto as a surprisingly active world, with mountains of water ice, plains of nitrogen ice, and a thin atmosphere that freezes and falls as snow when Pluto moves farther from the Sun. Pluto has 5 moons, the largest being Charon, which is so large relative to Pluto that they form a binary system, orbiting a point between them. Pluto is cold, distant, and small, but it captured human imagination, and its exploration was a reminder that even the small, remote worlds deserve our curiosity. Pluto is a world of ice and rock, spinning in the dim light of a distant sun, a reminder that the solar system's edges are not empty, but full of small, complex, and beautiful worlds. The solar wind is a stream of charged particles, mostly electrons and protons, flowing outward from the sun at hundreds of kilometers per second. It's produced by the sun's hot outer atmosphere, the corona, which is so hot that the sun's gravity can't hold it. The solar wind fills the solar system, interacting with planets, moons, and other bodies. Earth's magnetic field deflects most of the solar wind, but some particles are funneled toward the poles, where they collide with the atmosphere, creating auroras, the northern and southern lights. These shimmering curtains of light, green, red, purple, are one of nature's most beautiful displays, a visible connection between the sun and Earth. The solar wind also defines the heliosphere, a bubble around the solar system where the sun's influence dominates. Beyond the heliosphere lies interstellar space, the realm between the stars where the Voyager spacecraft now travel, humanity's most distant emissaries, carrying messages into the cosmos. Auroras occur on other planets too. Jupiter and Saturn have auroras far more powerful than Earth's, driven by their strong magnetic fields and interactions with their moons. Io, Jupiter's volcanic moon, ejects sulfur and oxygen into space, which ionizes and spirals along Jupiter's magnetic field lines, crashing into the atmosphere and creating auroras. Uranus and Neptune, with their tilted magnetic fields, have auroras that wobble and shift as the planets rotate. Even some exoplanets may have auroras, visible in certain wavelengths, hinting at magnetic fields and atmospheres. Auroras are universal, a natural consequence of magnetic fields and energetic particles, and they're a reminder that the phenomena we admire on Earth, the lights, the colors, the beauty, are part of a larger cosmic pattern, occurring wherever the conditions are right, a shared feature of planetary systems across the galaxy. The heliosphere, the sun's protective bubble, extends far beyond the planets, perhaps 100 astronomical units or more, depending on the solar wind's strength and the pressure of interstellar space. At the heliopause, the boundary where the solar wind meets the interstellar medium, the Sun's influence ends. Voyager 1 crossed the heliopause in 2012, and Voyager 2 in 2018, becoming the first human-made objects to enter interstellar space. They're still sending data, though their power is fading. They'll fall silent by the 2030s. Beyond the heliopause, space is not empty but filled with gas, dust, cosmic rays, and the magnetic fields of the galaxy. It's the space between stars, vast and cold, but not lifeless. It's the medium from which new stars will form, the reservoir from which the galaxy draws material for creation. The heliosphere is our local bubble, a small haven in the galaxy, and stepping beyond it is a milestone, a moment when humanity touched the greater cosmos. The cosmic web, that vast network of filaments and voids, is shaped by dark matter and gravity over billions of years. Computer simulations can model the web's formation, starting from the tiny fluctuations in the early universe and letting gravity amplify them over time. The results match observations remarkably well, showing the same web-like structure. These simulations help cosmologists understand how galaxies form and evolve, how structure grows, and how dark matter and dark energy influence the universe. They're virtual universes, evolving according to the laws of physics, and they're powerful tools for testing theories. The fact that simulations and observations agree so well is reassuring. It means we understand, at least in broad strokes, how the universe works. These simulations are also beautiful, abstract art created by equations and computation, colorful maps of dark matter density, showing the invisible scaffolding on which galaxies hang. It's a blend of science and aesthetics, revealing the universe's hidden architecture. Gamma-ray bursts are the brightest explosions in the universe, releasing as much energy in a few seconds as the sun will in its entire lifetime. They come in two types: short bursts, lasting less than 2 seconds, thought to be caused by colliding neutron stars, and long bursts, lasting more than 2 seconds, associated with the collapse of massive stars into black holes. The gamma rays are emitted in narrow jets, beamed toward us, so we only see a burst if we're in the line of fire. If a gamma ray burst occurred in our galaxy, pointed at Earth, it could be catastrophic, stripping away the ozone layer and exposing the surface to harmful radiation. Fortunately, such events are rare and most occur in distant galaxies. Gamma-ray bursts are laboratories for extreme physics, where matter is accelerated to near light speed, and studying them pushes the boundaries of our understanding. They're violent, brief, and brilliant, reminders that the universe is still capable of surprising us with its power. The concept of dark flow refers to the observed motion of galaxy clusters toward a particular region of the sky, seemingly pulled by something beyond the observable universe. This motion is controversial and not yet confirmed, but if real, it would suggest large-scale structure or mass beyond what we can see, hinting at a universe far larger than the observable portion. It's one of many mysteries at the edge of our knowledge, a tantalizing clue that there's more to discover. Cosmology is full of such puzzles, anomalies in data, unexpected observations, questions without answers. Each one is an invitation to look deeper, think harder, and remain open to the possibility that the universe is stranger than we imagine. And even if dark flow turns out to be a measurement artifact, the search for answers is valuable, refining our methods and deepening our understanding. The universe rewards curiosity, and every question, answered or not, brings us closer to the truth. The multiverse idea, while speculative, has several forms. The level I multiverse is simply the idea that space is infinite, so beyond our observable horizon, there are other regions, other universes in the sense of causally disconnected regions. Level II involves eternal inflation, where different regions stop inflating at different times, each becoming a universe with potentially different physical constants. Level III comes from quantum mechanics, the many worlds interpretation, where every quantum event branches into parallel realities. Level IV is even more abstract, proposing that all mathematically consistent structures exist physically, and our universe is just one mathematical structure among infinitely many. These ideas are difficult to test, and many scientists are skeptical, but they push us to think about what universe even means. Is it everything that exists, or just the part we can see? The multiverse challenges our assumptions and expands our imagination, even if we never find proof it exists. The observable universe has a redshift limit. Beyond a certain redshift, objects are so distant, and their light so stretched that they become undetectable with current technology. The highest redshift galaxies observed are seen as they were when the universe was only a few 100 million years old, still in its infancy. These galaxies are small, irregular, and actively forming stars, the building blocks of larger galaxies like the Milky Way. Observing them is like watching the universe's childhood, a time of rapid change and growth. The James Webb Space Telescope is designed to see even farther, pushing the redshift limit and revealing the first stars and galaxies. Each observation is a step back in time, a glimpse into eras we can never visit except through light, and each new image rewrites the story of cosmic history, filling in details and revealing surprises. The universe's past is written in light, and we're learning to read it. The concept of time's beginning is philosophically challenging. If time itself began with the Big Bang, then asking what came before is like asking what's north of the North Pole. The question doesn't apply. Yet it's hard to resist the impulse to ask. Some cosmological models propose scenarios where time existed before the Big Bang, cyclic models, bouncing universes, or emergent spacetime from quantum foam. Others suggest our universe is part of a multiverse where time has different meanings in different regions. We don't know if these models are correct or if they're even testable. What we do know is that within our universe, time has a direction, an arrow, flowing from past to future, and that the universe has a finite age. Beyond that we enter speculation, the frontier where science meets philosophy, and both remind us that some questions may not have answers, or at least not yet. And that's okay. Mystery is part of existence, and there's peace in accepting that not everything can be known. And so here we are at the end of our journey through the cosmos tonight. We've traveled from the Big Bang to the edge of the observable universe, from the smallest quantum fluctuations to the largest structures in existence, from the births of stars to the quiet deaths of white dwarfs and the violent explosions of supernovae. We've touched on dark matter and dark energy, those invisible forces shaping the universe, and we've wondered about the possibility of other worlds, other life, perhaps even other universes beyond our own. The cosmos is vast, mysterious, and beautiful, and I hope that exploring it with me tonight has brought you some sense of peace, of wonder, of connection to something larger than the worries and challenges of everyday life. Cosmology, at its heart, is the study of everything: the universe's origin, its structure, its evolution, and its ultimate fate. But it's also deeply personal because we are part of that story. Every atom in your body was forged in the heart of a star, scattered into space by stellar winds and supernovae, and eventually gathered into the cloud that became our solar system, our planet, and you. You are made of stardust, quite literally, and when you look up at the night sky, you're looking at your cosmic family, the elements that built you shining in distant suns. There's a profound connection there, a reminder that you're not separate from the universe, but an integral part of it, a way for the cosmos to know itself. The universe has been unfolding for nearly 14 billion years, and in that time it's created galaxies and stars, planets and moons, and on at least one of those planets, life arose, evolved, and eventually became conscious, aware, able to look back at the universe and ask where it came from. You are that awareness. You are the universe thinking about itself, asking questions, seeking answers, marveling at its own complexity and beauty. And even if we're the only ones, if Earth is the only place where consciousness has emerged, unlikely as that seems, then that makes you even more precious, a singular miracle in a vast, indifferent cosmos. But I don't think we're alone. The universe is too large, too full of possibilities, for life to have happened only once. Somewhere out there under alien skies, perhaps other beings are looking up and wondering the same things you've wondered tonight. The future of the universe is uncertain. It may expand forever, growing cold and dark in a heat death trillions of years hence. It may be cyclic, collapsing and rebirthing endlessly. Or perhaps something we haven't imagined will happen, some new physics or cosmic event that changes everything. But whatever the far future holds, it doesn't diminish the now. You are alive in a time when stars shine, galaxies collide, and the universe is rich with complexity and beauty. This is the golden age of the cosmos, the era of stars and planets, of light and warmth, and you're here to experience it. That's not nothing. That's everything. As you rest tonight, let the vastness of the cosmos be a comfort rather than a source of anxiety. Yes, you're small in the grand scheme of things, but smallness doesn't mean insignificance. A single photon from a distant star can cross the universe and touch your eye, connecting you across space and time to something ancient and far away. A single thought can encompass galaxies, imagine infinities, and ponder the deepest questions of existence. You contain multitudes, even as you rest here, breathing slowly, letting the universe hold you gently in its gravitational embrace. Thank you for spending this time with me tonight, for letting me guide you through the wonders of cosmology. I hope you found some peace, some wonder, and perhaps a new appreciation for the universe and your place within it. If you enjoyed this journey and you'd like to support the channel, please consider subscribing, leaving a like, or sharing this video with someone who might need a peaceful cosmic bedtime story. And if there's a topic you'd like me to explore in a future video, leave it in the comments. I read every one, and your suggestions help shape what I create. But for now, let go. Let your body rest. Let your mind drift. The universe will be here tomorrow, still vast, still mysterious, still beautiful. The stars will still shine, the galaxies will still turn, and you will wake refreshed to a new day under the same sky that has watched over humanity since the beginning. You're safe. You're part of something infinite and eternal. And for tonight, that's all you need to know. Sleep well, dear traveler. The cosmos will keep watch while you rest. Good night.